Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. Well, to access the notebook for today's session, you can access course page on my personal website, arifbut.me. The other way is to download all the notebook files from course GitHub account, ArifPUCIT. And all the notebooks for this course are housed in this public data science repository. Well, this is a Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.14 of the 6th module, Machine Learning, for the course titled Tools and Techniques for Data Science. Well, today we are going to talk about different cross-validation techniques. Fine, here is the agenda for this notebook. And my dear students, let me start by visiting this link of scikit-learn regarding cross-validation. Well, cross-validation are actually statistical methods to evaluate generalization performance of machine learning models in a more stable and thorough way than a simple splitting of data into a training and a test set. And we all are used to of using this train test split method. Well, my dear students, there are a variety of cross-validation techniques that you can read about on this page, like the K-fold and the stratified K-fold, repeated K-fold, repeated stratified K-fold, shuffle split, stratified shuffle split, leave one out, leave P out. We have group K-fold, group stratified K-fold, which are used in image and speech processing. And of course, we do have the time series split that is used for splitting the time series data. Well, my dear students, all these techniques split the data repeatedly so that you can truly evaluate your machine learning model. Well, cross-validation is also used for hyperparameter tuning, as well as comparing the performance of different machine learning models on a dataset. And I'm sure after watching this video, if you fall back to this page, all this will make sense to you. Let me fall back to the notebook. Okay, so today, first I will set the stage right by giving a quick recap of why and how do a simple train test split works, by giving its pros and cons as well. Then we will actually do a scuba dive into three most famous cross-validation techniques: K-fold, stratified K-fold, and time series split. So fill up your oxygen tanks and get ready for jump. Okay, my dear friends, let me start with a quick recap of evaluating a machine learning model. And this is a bad approach which I'm showing you right now. We have never used this approach in any of our previous sessions, and this is to use all the available data for training the model and then test or evaluate the trained model using the same data. Consider this real life example where a math teacher trains his or her students on a set of, let's say, 100 sample math questions, and later tests the student using, say, 5 questions from the same set. A well-trained student might get 100% marks if he or she has just memorized all the questions and will not perform well, of course, on new or unseen questions. And this is what we have seen in our previous session, which is a scenario of overfitting. My dear friends, instead of using this terrible approach throughout our session, so far we have been splitting the available data into two parts and two sets as shown in this image. You can see now the math teacher has actually divided all the 100 questions into two sets, a training set containing 80 questions on which the students are trained during the classes, and a test set containing 20 questions on which the students' understanding of the concepts are tested or evaluated. Well, 2 points to keep in mind during this split are, first of all, before doing this split, the data or questions need to be properly shuffled. A wrong shuffle may cause problems. Suppose there are 100 questions which are related to calculus, algebra, and probability. And somehow after the split, this training data has no questions of probability. Rather, all the probability questions are there in this test data. So students will fail as they are not trained on the probability questions. Rather, they are trained just on the calculus and algebra questions, and they are tested on the probability questions. So the students might fail. The second point to keep in mind is the ratio of this split. Well, in most of the cases, we do a 80-20 or maybe a 70-30 split into training and testing data respectively. Well, it depends on the overall availability of the dataset as well. So these are the 2 points the math teacher must keep in mind while splitting the overall question pool into a training set and a test set. One more point the math teacher should keep in mind during the collection of these 100 questions is that these 100 questions should be a true representation of all the concepts related to calculus, algebra, and probability. And the dataset should be balanced, that is, containing roughly equal proportion of the questions from calculus, algebra, and probability. Well, this is the code cell that shows how it works in Python. Suppose this X is our dataset containing indices of 100 questions, 1 to 100, let's say. I'm using the train test split method and passing it this X with a test size of 0.2. I have set the shuffle to false. This method will return a two-valued tuple, xtrain and xtest, containing the indices of the training questions and test questions, which I am printing over here. Let me execute this. And let me execute this again. And again and again. You see, since the shuffle is false, so you're getting the same set of questions or question numbers in the training data and the same in the test data. Let me make this false to true now and run it again and again and again. You see, each time we are getting a random split from the available data to the training and the test data. I hope this is clear to you all. Well, my dear friends, let me extend this real life example to a scenario of machine learning. Consider the same old advertising dataset that we have been working in our previous sessions, having 3 input features, showing expenditures spent on TV, radio, and newspaper advertisements in thousands of rupees. This output column sales shows the number of items sold in 1000 units. And of course, there are 200 total rows in this dataset. We are using the same train test split method, which is shown in orange color over here. But this time I'm passing it 2 arrays, an array of input feature X and an array of output features Y. Instead of 2, the method is now returning a 4-valued tuple. if you see in this image, the training data shown in green over here will have shuffled 160 rows of X called the X train, and their corresponding 160 rows of Y called the Y train. Similarly, this blue box represents the test data having shuffled 40 rows of X called the X test, and their corresponding 40 rows of Y called the Y test. Well, since this is a regression problem, because we want to predict the sales, a continuous value based on the expenditures spent on TV, radio, and newspaper advertisement. So let's create an instance of a linear regression model and call the fit method on this model by passing it the training data set X train and Y train. This training phase is implemented in Python code shown in orange color over here. Once we are done with the training of the model, it is time to evaluate it using the test data. Well, we have seen different evaluation metrics for regression algorithms, but right now I'm computing the R2 score, and we can compute the R2 score using either the R2 underscore score method of a matrix module of sklearn by passing it the original Y test values and the model's predicted values, which I am computing over here by calling the predict method on this trained model. Another simple way is to call simply the score method on the trained model and passing it the X test and the Y test. And these two lines of code, I hope, are making sense. And this is the code cell which actually perform all this. I hope I have discussed all this code. Let me simply execute it. So once I execute it, our model accuracy comes out to be 0.88. My dear students, let me execute this code again and again. You see, we are getting different scores. And the reason is, each time I am executing this code cell, due to this shuffle attribute set to true, we are getting different data values in the training set and test set. Therefore, each time we get a different R2 score. So one of the limitations of this train test split technique is we are evaluating our model on just 20% of the data. It would be far better if we somehow can evaluate our model on the remaining 80% of the data as well, which is not right now used in the testing. And this is actually where the idea of K-fold cross validation comes in. Okay, my dear students, let me use this mglearn package written by Andreas Müller for his book Introduction to Machine Learning with Python. To give you an overview of K-fold cross validation, you can install it using pip and do visit this GitHub link if you are interested in the code of this library. And over here I'm using the plot underscore cross validation method of the plots module of mglearn. Okay. This is the entire available data set, which is by default divided into 5 chunks or folds. So in this case, the value of K for the K fold is 5. So this is a 5-fold cross validation. You can think of it as calling the train test split 5 times on this data set. This is split 1, this is split 2, this is split 3, this is split 4, and this is split 5. and the entire dataset is divided into 5 folds: fold 1, fold 2, fold 3, fold 4, and fold 5. In this split 1, the first horizontal rectangular box, this shaded fold 1 is considered as the test data. We train the model on the remaining folds and then test it on this fold 1. In this split 2, this shaded fold 2 is considered as the test data. We train the model on the remaining 4 folds and evaluate it using this fold 2. And this process is repeated for all these 5 splits. And finally, we get 4 different models, and we can compute the accuracy of those 4 different models. Let me show you how this K-fold actually works in Python. For this, we have to import the K-fold class of model selection module of sklearn. Suppose X contains the indices of the dataset having, let's say, 10 data points, 0, 1, 2, 3, so on to 9. This K-fold method will create an instance of K-fold cross validator. I want to do 5 splits and have set the shuffle argument to false. Let me make it to false first for easy understanding. Then I have called this split method of this K-fold cross validator object, and I have passed it X inside our loop, which will return me a 2-valued tuple. And of course, this loop will run 5 times. And in each iteration, I am actually printing the train and test indices. I hope this code is making sense. Let me run it. You see in the first split, indices 0 and 1 are in the test set, while 2, 3, 4 and so on to 9 are in the training set. Similarly, in split 2, the indices 2 and 3 are in the test set, while 0, 1, 4, 5, 6, 7, so on to 9 are in the training set. Let me make this shuffle argument to true and run this code multiple times. You see now the data is shuffled before the splits. However, the test data is still the union of the entire dataset. So that means we train 5 models, compute their accuracies, and finally compute the mean of those 5 accuracies. That mean will be of all those 5 models which are tested on the entire dataset. And this is how we overcome the limitation of a simple train test split technique. Similarly, let me change this split argument. Its minimum value has to be 2, as you need to make at least 2 splits. So these are the 2 splits. Its maximum value in this case can be, I think, 10, where we have 10 splits. And in each split we have 9 values for training and 1 for testing. And this is also called leave one out cross validation. I hope this is making sense. Okay, my dear students, let me move ahead and apply this K-fold cross validation on the advertising dataset again. So these are the 200 observations of the advertising dataset. First, we need to create K-fold cross validator and tell it that we want to do a 5-fold cross validation. These 2 lines of code in orange at the very top will do this job. We further need to, of course, call split method on this K-fold cross validator object, and pass it this entire data frame. We can always pass X and Y to it. And this will return us the indices for the training and the testing data. And the loop, the code I have not shown over here, the loop will run, of course, 5 times, and each time we need to train the model on the training data, test the model on the validation or test data, and compute the model accuracy, that is the R2 score. So we will have, after this loop finishes, we will have 5 R2 scores, and by taking the mean of all 5 scores, we get the true accuracy of the model, which is now tested on the entire dataset. My dear students, instead of doing all this programmatically using a loop, we can of course use the cross-val score method or maybe cross-validate method. I hope this is making sense. This is what I have shown pictorially over here. You can see this is the first split in which the first fold is the validate portion of the data and the remaining 4 folds are the training portion of the data. In the second split, this is the validate part and the remaining 4 folds are the training part. And we run our model on all these splits. We get 5 different R2 or accuracy scores, and probably these are the scores which this method will return. I hope this is making sense. Let us do all this practically for a crystal clear understanding. Okay, so let me first read the dataset using the read CSV method into a pandas data frame. I am separating the input feature X and the output label Y. Then I am creating the K-fold cross validator object for 5 splits. Over here I am entering in a loop and simply prints the train and test indices of the 5 splits. Let me execute this code. Great. Okay, so this is the split 1 and these are the test indices for split 1. This fold 1 contains 40 indices from 0 to 39 for testing purpose, and the remaining 4 folds contains 160 indices from 40 to 199 for training purpose. Similarly, this is the split 2, which has fold 2 containing indices 40 to 79 for the testing purpose and the remaining indices for the training. My dear students, please pause the video and see how the training and test indices have been divided in all these 5 splits. Okay, now let us calculate the R2 score by training and testing using the linear regression model for all these 5 splits. For this I have defined a function get_score, which is passed a model that will be a linear regression in this case, along with the X train, X test, Y train, and Y test. The function calls the fit method on the model and passing it the X train and Y train. And finally, it returns the R2 score by calling the score method on the trained model and passing it X test and Y test. Let me execute this function, and now in this code cell over here, I am once again creating the K-fold cross validator object, calling split, and this is the line of our interest, these 2 lines. Well, this first line inside the loop is actually using the train and test indices returned by the split method to get the actual data inside the X train, X test, Y train, and Y test. I hope this first line is making sense to you. I've used the lock method with X because X is a data frame and I have not used it because y is probably a series and or an array. It will work on it like that. Well, this second line inside the loop is calling the getScore method or function by passing it the 5 required arguments. The first is the model, which is an instance of linear regression model in this case, and the remaining 4 are xtrain, xtest, ytrain and ytest. So each time this loop executes, this function will be called and it will return the score, and I am appending that score in an empty list named score list. So once this loop is done, this scores list will be having 5 scores, and that I am printing over here. So these are the 5 scores and this is the mean score. So our linear regression model, the mean accuracy comes out to be 0.887. I hope this makes sense. Well, my dear students, sklearn provides us cross-val score method, using which we can perform the same task using a single line of code. So this is the cross-val score method. The method is passed an instance of the model, of course, the input feature x, the output label y, and the number of splits, which can be an integer value maybe, or an instance of the kfold object. Right now I am passing the kfold object, instance of the kfold object to it, and it returns an array containing R2 scores for all the 5 splits in this case. Let me simply execute this. The same answer, same mean R2 score that we have computed using this loop, that is 0.887, and this is also 0.887. So this is what a cross-val score is. Most of the time for simple code we use cross-val score. Like cross-val score, there is another related method that is cross-validate. My dear students, like cross-val score, which returns just the test scores, one can use this cross-validate, which actually is more powerful and returns a dictionary having multiple information. You can see the code is almost same. Let me show it to you like this. So you can compare. We have just made this change. Let me execute this code. You see it has returned a dictionary. I have printed it. There are 3 key value pairs in it: the fit time, score time, and test score. For better visualization, let me create a data frame from this dictionary. So these are the 5 fit time, score time, and test scores when the linear regression model is run on this dataset. Well, there are some other arguments as well, which I just want to use. One is the return underscore train underscore score argument, whose default value is false. I have set it to true now. The other is return underscore estimator argument. Default value is false. I have set it to true. Let me execute this again. Now you see we have some additional information, and that additional information is we are getting the train score as well now, and we are getting the estimator as well. Well, great. So this is what cross-val score and cross-validate method do. I hope this makes sense. Well, my dear students, the scoring argument of cross-validate that I have not used over here. Another difference of cross-validate from cross-val score is that it allows specifying different metrics for evaluation using its scoring argument, this argument, which can be a single metric or a list of metrics. Over here I have given a list of two different metrics. By default, cross-validate method uses the chosen model's default scoring metrics. And of course, for a linear regression model, the default scoring matrix is R2 score, which we have got over here. So this is the R2 score. And if you want to change it to some other scoring metric, you can write the scoring metric over here and you will get the result. So you see we have got the negative mean absolute error as well now. Well, my dear friends, do explore different scoring metrics at your own time, and let me move ahead. Well, in literature, my dear friends, you may come across an extension of K-fold cross-validation, which I have tried to describe in this image. You first perform actually a train test split on the entire dataset and keep, say, 80% data for the training and 20% for the testing, or you can call it holdout data. We do a K-fold, say 5-fold split on this training data only, and do the training and testing on all these splits as done before. Once you are satisfied with the performance or accuracy of your model, you finally evaluate that model using this test or holdout data. And this is the final accuracy of your model that you should report to your project manager. I hope this makes sense. Well, my dear friends, one last point is that once you are done with all these tasks, you train your final model on this entire data set before you deploy it or ship it to your client. Okay, so far so good. My dear friends, the standard K-fold cross-validation works perfectly fine for regression tasks. However, for classification tasks, it is better to use stratified K-fold. And let me describe this with the help of two examples. And let me first load this Iris dataset. Let me execute this column so that you can understand it. So this is the Iris dataset, having 4 input features: sepal length, sepal width, petal length, and petal width. The output label target specifies 1 out of 3 species of iris flower, 0 for setosa, 1 for versicolor, which is not visible over here, and 2 for virginica. And there are a total of 150 rows in this dataset. I think we have talked about this dataset in our previous session somewhere. Let me show you the array. Let me execute it like this. So this is the target array Y, which I have kept in this Y. So this target column, this column Y, contains 50 zeros, that means setosa, 50 ones, that means versicolor, and 52s, that means virginica. So label encoding has been already done on this column. And do note that they are in exact sequence. That is, first 50 observation belong to class 0, setosa. Next 50 observations belong to class 1, that is versicolor. And last 50 observations belong to class 2, that is virginica. This is important. Now let me describe as how K-fold and stratified K-fold may work on this dataset using mglearn, this plot of mglearn. Well, this upper image shows how a 3-fold cross validation will work on this dataset, having sorted class labels. In this first split, this first rectangle over here where my mouse is hovering, the training will be done on fold 2 and fold 3 containing 100 observations related to versicolor and virginica. And when this will be training will be done, this will be tested on the remaining 50 observations which belong to iris setosa. And of course, we will get a test score of 0 because the model has been trained on the data of versicolor and virginica and not on setosa. Similarly, in this split 2, the training will be done on fold 1 and fold 3 containing 100 observations related to iris setosa and iris virginica. And once this model is trained, it will be tested on fold 2 containing 50 observations related to iris versicolor. And of course, we will again get a test score of 0. And the same will happen for this split 3 as well. My dear students, the solution to this problem is stratified k-fold cross validation. And this lower image shows how a stratified 3-fold cross validation will work on iris dataset. Note that in each split, the test or validation data contains 50 observations, of course, but this time it contains approximately same amount of strata of samples from all the 3 classes. So in split 1, we have a portion from iris setosa, we have a portion from iris versicolor, we have a portion from iris virginica. I hope this is making sense, and the same will happen for split 2 and split 3 as well. If this is not clear, my dear friends, please rewind this part of the video and listen it again. Let me move ahead and do this practically. Okay. Let me once again load this data set, that is the iris dataset. Now I have X containing the input features and Y containing the target. This code cell contains almost the same code as discussed above, in which I discussed the advertising dataset, which was a regression problem, and we used linear regression model over there. You see, this is the get score method, no change, and this is the code which we have seen before. However, since this is a classification problem, so instead of using the linear regression model, I'm using logistic regression model. And I'm passing this logistic regression model to this get score function. Another change is that over here we are making 3 splits while creating the k-fold cross validator object, and rest all the code is same. Let me execute this code, and you see, as expected, we got an accuracy or R2 score of 0 for all the 3 splits. Over here the shuffle argument is false, so that is why it has done exactly like this. This was the first fold, this was the second fold, and this was the third fold. In split 1, this fold 1 was used for testing, while fold 2 and 3 were used for training. So that's why the model was not trained on iris setosa data. So that's why we get accuracy of 0. Let me make this shuffle argument to true and run it again and again and again. My dear friends, you can, if you set this shuffle argument to true, it may solve the problem a bit. However, the groups might not be balanced in this case. I will talk about the balancing of the groups a bit later. Anyway, let us now see the cross-val score. To do the same task, let me execute it. So you see, whether you do it using a loop programmatically or you use the cross-val score, the output is 0. My dear friends, let me add one more point over here, and that is, instead of passing kfold object to this cross-val score method, you can simply pass it an integer value showing the number of splits. Let me pass it 3. In that case, this cross-val score method will use a kfold for regression task and stratified kfold for classification task. Let me repeat this point. If I am passing an integer value to this argument CV of this cross-val score method, if this model is a regression model, it will use kfold, and if this is a classification task or classification model, it will use stratified kfold. So now if I will run it, I will not get a result of 0. Let me run it. Great. So now it is not using this kfold, it is using stratified kfold, and if I specify kf over here, now it is forced to use kf for this classification model, and now the result will be 0. Great. I hope this makes sense. Okay, now let us use the stratified kfold on the Iris dataset. The only difference in this code cell is that I am creating a stratified kfold object, stratified kfold cross validator, and I'm calling the split method now on its instance. Rest everything is same. Let me just execute it. So we are getting a good score on all the 3 splits. And my difference, similarly, we can call this cross-val score as well and pass it the stratified kfold object, and we will get, of course, the same results. But of course, this is a far simpler code as compared to this. Okay, my dear friends, let me create an imbalanced dataset now, as shown in this image, having 2 classes. 70% observations belong to this class, let's suppose 0, and 30% observations belong to this class 1, let's suppose. The stratified kfold cross validation partition the data such that the validation data has an equal number of instances of the target class label. So this is what actually stratified kfold is. If you see this row 1, this is split 1, the orange box is the test or the validation data, and the remaining 4 blue boxes are the training folds. Note that in all these folds, the data has same proportion of observations from both the classes. Okay, I hope this makes sense. Let me actually create a synthetic dataset, an imbalanced synthetic dataset using the make classification method of the datasets module of sklearn, having 1000 samples, 4 input features, and 2 target classes. Using this weights argument, I am actually creating an imbalanced dataset in which 95% observations belong to one class and just 5% belong to the other. Let me execute this. Let me confirm this by just getting the X. So these are the input features, 4 input features, 1, 2, 3, 4, and of course there are 1000 observations. Let me check out the let's say first 100 values of the output label. So these are the first 100 values out of the 1000 output labels. You see most of the observations belong to class 0. Okay. Let me check out the length as well. Length of this y, where y double equals let's say 0. So this will give me all those locations where we have a 0 in y, and I'm computing the length of it. So it is 944. Makes sense, I think. Let me check out the count where we have y is equal to 1, and that is 56, and that roughly makes 95% and 5%. I hope this makes sense. So that means the count of observations that belong to class 0 are 944, and the count of observations that belong to class 1 are 56, which is roughly 95% and 5% respectively of course total of 1000 observations. Now let me move ahead and split the dataset using K-fold and stratified K-fold. Let me just execute both these code cells so that you can compare them yourselves easily. And so this is the output of using K-fold. So I have used K-fold, and these are how the data is distributed among the different splits. Note that I have made 8 splits, so these are the 8 splits. If you see the test or validation portion of these 8 splits, you can note that this split 2 in split 2 over here, which I have highlighted, has just 4 observations that belong to class 1, and this split over here has 10 observations which belong to class 1. So in this case, the model accuracy will not be the proper reflection of how well the minority classes are being predicted, because we have different number of minority classes in each split. Over here I have 10 observations belonging to class 1. Over here I have 4 observations belonging to class 1. Over here I am having 8 observations belonging to class 1. I hope this makes sense, and this is because of the K-fold. And stratified K-fold of course comes for the rescue, and if you see the output of this code cell, you can observe that the proportions between the classes are the same, almost same in each fold as they are in the whole data set. So we have 7, 7, 7, 7 and so on. So this ensures that one particular class is not over present in the train or the test data. I hope this makes sense. Let me move ahead. Okay, fine. My dear friends, be watchful when applying cross-validation on time series data. The techniques discussed above may not work well on time series data. To me, the best technique to cross-validate time series data is rolling cross-validation, which in scikit-learn can be implemented using the time series split. And let me describe this using this image. Let's suppose that we have 100 years of climate data, and in this left image I do the standard K-fold cross validation, say 5-fold cross validation. Excuse me. Well, if I do not do the shuffling, then this first split, it appears that I am training the model on the future data. So this is the future data, of course. This is time series data. This is the future data. I am training my model on this future data, and I am testing it on the past data. And this problem will persist even if I do a random selection of this test data as well. So shuffling this data will mess up with the timestamps associated with each data item, and of course it will disrupt the order of the events. So to summarize, if I use K-fold to cross-validate time series data, there is a chance that we train the model on future data and test on past data. And of course, this will break the golden rule in time series, and that says peaking in the future is not allowed. Well, solution to this problem is time series split, which is described in this right image. We create the folds or subsets in a forward chaining fashion. My dear students, in time series split cross validation, we take a small subsample of the data, keeping the order intact for training of the model, and then try to predict the immediate next sample for validation. And this is shown in this first split, and in the next split, and in the next split. So we are never peaking in the future. We are training on the past data and predicting the future data. I hope this makes sense. Let me show you this in Python over here. First, I have imported the time series split cross validator from model selection module of sklearn. I have created over here 3 input features, and there are 10 observations. And suppose this is a time series data, although it is not. Of course, after this, I have created a time series split object and have run the loop by calling the split method on TSS and passing it the data, as we have been doing before as well. Well, inside the loop, I am just printing the indices of the training and the testing data. Let me just execute it. So you see in split 1 over here, we have initial 4 observations as a training set, and the 5th and the 6th observation as test set. In split 2, 0 to 5 are the indices of the training data, while 6 and 7 are the indices of the test data. And of course, this process goes on. I hope this makes sense. Well, my dear friends, after understanding and practically implementing different cross-validation techniques discussed in today's session, I think you can explore the rest at your own. So that is all for today's session. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.